In the next block of segments, what we're going to do is talk about some of the basic types inside Haskell. We'll start off by talking about the Booleans, but then we'll talk about numeric types, we'll talk about characters and strings. So these are the fundamental types from which all the other types that we work with get built. Let's start with the Booleans, because they are such a nice type to discuss. They're named in honor of George Boole, who was a famous autodidact mathematician and logician from the 19th century, who wrote the seminal book, The Laws of Thought. And that, because of that, he is one of the people who's responsible for the fundamentals of computer science. Because what he did was see a way of looking at logic as something mathematical, as something algebraic. And what he did was he introduced the idea that there were these two values. The truth values, true and false. True is representing something that is the case, and false is representing something that isn't. And any statement in his view of logic can be given either the value true or the value false. So the type of Booleans consists of those two values, true and false. On top of those are provided three operations. You can take the conjunction, the AND of two values to give a Boolean value. You can take the OR of two values to give you a Boolean value, and you can take the negation, or you can take not a value. Now, I'm writing here the types of the AND operator, which is two ampersands, the OR operator, which is two vertical bars. In order to write their type down, I put them in parentheses because that turns an infix operator into a prefix function. So then I can write its type as the type it has as a function. But when we write them down, we'll write, if we want to combine, take the AND of two Booleans, we write the first Boolean and the second. So there we have the three operators, and they get defined by what's called a truth table. And what that does is, if you look at the value of A and B, this table gives you the value that has for all the possible combinations of inputs. Now, because there are two Boolean values, each input can be one of two things, and there are two inputs, so it's 2 to the power of 2 choices for the first times 2 choices for the second. So there are 4 lines in this truth table. But in general, if there are n arguments to a Boolean function, there will be 2 to the n, 2 to the power of n inputs, lines on that, combinations of inputs, and so lines in this truth table. Now you can see here that what the value of A and B is true only when both A and B are true. The value of A or B is when either A is true or B is true or both are true. And the value of not A is false when A is true and true when A is false. So those are the standard Boolean operators. Now let's start making some more definitions for ourselves. And let's think about a particular example of a function. And this is called exclusive OR. Now here's a menu from a restaurant I found on the internet. If you look at the main courses, you are offered chicken or sea bass or rigatoni. And when you see that or on a restaurant menu, it means you can have one of these, but not all three. It means you must make a choice, an exclusive choice of precisely one of those. So this is what's called exclusive OR. The OR we showed on the previous slide was inclusive. It was true if both A and B are true. And what we want now is an OR that is true only when precisely one of them is true. Let's see how we can define that. Here's one way of defining it. You can say we want X or Y, that's the top path through the graph, and not X and Y. So here we've got the definition, and what's nice about this, it uses all three Boolean operators. It says X, exclusive OR of X and Y is X or Y has to be true, and X and Y has to be false, i.e. not X and Y has to be true. So that's one way of defining exclusive OR using the Boolean operators in Haskell. But what I want to do now is do something a bit different. I want to show you that when you write a definition in Haskell, you don't always have to put variables on the left-hand side of a function definition. You can do what's called pattern matching. And here is another way of defining exclusive OR. And this says it gives 4 cases, 4 equations, one for each combination of arguments. So it says when exclusive OR of true and true is false, exclusive OR of true and false is true, exclusive OR of false and true is true, and exclusive OR of false and false is false. And you can see it's true only on the second and third lines where one of the arguments is true and the other one is false. So you can write a definition out like that in full. Now what we've got here is the first line gives the answer false, the second line true, the third line true, and the fourth line false. We could rearrange those and say, first of all, what the arguments are for the result true, and that's when one argument is true and the other is false, or vice versa. And then you can see that all the other options give the result false. So we could write this. We could say whatever value of x or whatever value of y, if the first 2 cases don't hold, then the answer is false. So we're saying, and because those are variables x and y, they could be anything. And because the way that these definitions are interpreted, it's the first one that applies holds. So the first 2 equations cover the case where exactly one value is false, and then the remaining equation covers all the other cases. Now we can also replace x and y here by what's called a wildcard or underscore. The reason we do that is because we don't actually need to know what x and y are. They could be anything. And so because we don't use their value in defining the right hand side here, so we can just say wildcard, exclusive OR of anything and anything as long except covered by the first 2 cases gives the answer false. So when we do pattern matching, we can have this kind of catch-all case at the end. We're saying whatever else holds, the answer is false. So here we did pattern matching over the full, over the 4 options. We said for both arguments, whether we gave a pattern, we said whether it's the value true or the value false. But we can also do something else. So let's go back to the first definition and take a look at those first 2 lines. When the first argument is true, how do you get the results from the second? When the second argument is true, the result is false. When the second argument is false, the result is true. So you can condense those 2 into a single line saying if the first argument is true, the result is not the second argument. And if you look at the other case where the first argument is false, you see the result is the argument y itself. So here you see an example of pattern matching where you mix up a pattern for the first argument and a variable, a constant for the first argument and a variable for the second. So pattern matching is a really nice way of describing definitions, and we'll use it all the time through our definitions in Haskell. But the simplest sorts of patterns you can have are over Booleans, where for a particular argument, its value is either going to be true or it's going to be false. So we get these particularly nice forms of pattern matching, as you see here. Now, as an exercise, why don't you just stop the video and see if you can find 2 more different definitions of exclusive OR.